In our last class, we introduced the mesh analysis algorithm for the simplest circuits. Those are what we call type 1 circuits, where if you had current sources, they were always on the perimeter of the circuit. Voltage sources could be anywhere, but if you had current sources, they had to be on the perimeter of the circuit. Today, we're going to extend the mesh analysis algorithm and consider type 2 circuits, which are circuits where you have interior branch current sources. Let me first show you what I mean by interior branch current sources. So imagine you have a circuit here. This current source on the right is a perimeter current source. These were easy to handle because the value of that current source equals the value of this mesh current here. This current source is what we call an interior branch current source. Its value does not equal the value of either of the mesh currents it is connected to, that yellow one or that pink one. In fact, it's going to be a combination of the yellow mesh current and the pink mesh current. The difficulty here is we do not know the voltage across current sources when you're writing your KVL equations. And so when you try to write a KVL equation for either the yellow mesh or the pink mesh, you're going to come across a problem because you don't know what this voltage is. And we'll see that on the next page. This is similar to what we saw in nodal analysis when you had a floating voltage source. With a floating voltage source, you did not know what the current through the voltage source was, but yet you had to write a KCL equation. Here, you don't know what the voltage across the current source is, but yet you have to write a KVL equation. So we're going to see that we have a solution similar to the supernode. We have another superhero, this one called Supermesh, that will be used to overcome this problem. There is another method called a modified mesh analysis. This is a technique we're not going to teach in this course, but it's similar at least to the Supermesh analysis algorithm. So let's explain Supermesh a little bit. A supermesh is going to be a loop that encompasses multiple meshes, and it's a loop that is specifically drawn to avoid having to find the voltage across an interior branch current source. So the idea here is you sort of ignore that current source when you're creating the loop that you want to do KVL for. So let's look at this example on the left here. You have 4 meshes. A mesh here, second mesh, third mesh, and fourth mesh. So what happens if we try to write a KVL equation for mesh 1? So if we take mesh 1 and try to write a KVL equation, let's start at this point here and let's go clockwise. So if you do mesh 1 KVL, you hit a voltage source first, you know that, it's negative VA. The voltage across R1 is easy, it's R1 times I1. But what happens when you try to get to the current source? You do not know the voltage across it. You don't have a way you could express the voltage across that current source. So it's plus question mark equals 0. Likewise, if we try to do that for the pink mesh, you'd have the same problem. You could find the voltage across resistor R5. It's R5 times I3 minus I4. You could find the voltage drop across R4. It's just I3 times R4. But when you get to that third element, that current source IX, you don't know. For the green node, you don't have to worry about it because you don't have to write a KVL equation there. So because you have a perimeter current source there, we don't have to worry about the green mesh. And likewise, we don't have to worry about the blue mesh because there is no current source. But this source here is going to cause a problem. So the solution here is to do a super mesh. So rather than having the separate yellow and pink meshes, we're going to have a single mesh called a super mesh. We're going to pretend that current source didn't exist. So I have a grayed out here, and we're going to use this super mesh. Notice we still have 2 separate mesh currents, I1 and I3. You don't just create a single current, it's 2 separate currents, I1 and I3, but it's a single loop. And then we're going to keep this mesh and this mesh. So this yellow loop is what we now call a supermesh. But what we're going to see here is when we try to write our KVL equation, let's start at the same red node here. So the supermesh KVL we're going to find is doable. Starting at that red node, we hit the voltage source, so it's negative VA. The voltage drop across R1 is what? R1 times I1. Then you hit the R5 resistor. The voltage drop across that is what? The resistance times the current in the direction we're going. We're going in this direction. That's in the direction of I3. It's opposite direction of I4. So it's I3 minus I4. Now, of course, I4, where we know, is whatever this IY is. So you could write that as I3 plus IY. Why plus IY? Because I4 is equal to negative IY. Because I4 is a variable defined clockwise, and IY goes from bottom to top. So the bottom line is the voltage across R5 is R5 times I3 plus IY. And then finally, the voltage drop across R4 is the resistance times the current in the direction we're going, which is I3. We're back to where we started. We get 0. So notice we did not have to worry about this unknown voltage across IX. That's the advantage of using the supermesh. The problem with using the supermesh is just like when we used a super node, here we have two different meshes, the I1 mesh and the I3 mesh, but we only get one equation out of it. So you get one equation and two unknowns. How do we get our second equation? And that's going to be our source equation. So just like with floating voltage sources in nodal analysis, interior current sources in mesh analysis give rise to the need to use a source equation. The source equation is the equation that relates this specific current source to the two meshes that it's connecting. So the source equation in this case would be Ix, the current source value, it's in the direction of I3, it's in the opposite direction of I1, so Ix is I3 minus I1. So when you do super meshes, you not only have a supermesh KVL equation, but you will also have a source equation associated with every interior branch current source. Let's look at the algorithm. So the supermesh analysis algorithm is for type 2 circuits. Type 2 circuits are those with interior branch current sources. We're going to see that most of the steps are identical to what we had for type 1 circuits, but there are a couple changes and I'll highlight those. So the first thing you do is, if necessary, you redraw the network so you don't have any meshes overlap. Remember, mesh analysis only works for planar circuits, and so if you have a circuit that looks like it might not be planar but actually is, you can rearrange how the branches are laid out to show that it is actually a flat circuit. In this course, at least, I don't think you're going to have any problems where you actually have to redraw the network. We're always going to draw it so it's already flat. And of course, if the circuit is not flat, if it cannot be drawn two-dimensionally, you cannot use this algorithm at all. The next step is you look at all your meshes, all of these window panes, and determine whether that mesh current is known or unknown. So you want to identify known and unknown mesh currents. The way you do that is you look at each mesh and determine if there's a current source associated with the mesh. It's going to be one of two cases. It's going to be an exterior branch current source, in which case the mesh current is known. Those are the easy ones. If you have an interior branch current source, then you have to have a super mesh, and you're not going to know the specific mesh currents. Instead, you have the two variables. Once again, on this example here, you have two different mesh variables when you have a super mesh. If you have a mesh with no current source at all, then once again, you don't know the mesh current, so you assign a variable to it. So you're going to have three different situations. A mesh with a perimeter current source, those are the easiest. A mesh with no current source at all, those are your standard meshes. And then you're going to have meshes where you have an interior branch current source. That's when you're going to have to create your super meshes. Once you define your variables, you now write your equations. So the first thing you do, if you have any dependent sources, whether it's a dependent voltage source or a dependent current source, basically express each control variable in terms of the mesh currents. In other words, you do not want to be introducing additional variables into your equations. So if you have a controlling voltage or a controlling current, re-express those in terms of the mesh current variables that we established in step 2. Then you start writing your KVL equations. For every run-of-the-mill standard mesh, you write a KVL equation. For every super mesh, you write a KVL equation. Of course, you do that for the super mesh so you can avoid having to find the voltage across that interior branch current source. And finally, for every super mesh you have an interior branch current source, you write a source equation for that. So if you have 3 unknowns, you're going to end up with 3 equations. If you have 5 unknowns, you're going to end up with 5 equations, etc. So you compile the equations and you solve, either using Math 220 techniques or other techniques to solve systems of simultaneous equations. Finally, if necessary, these last 2 steps are if necessary, and that depends on what the problem is asking for. So if needed, once you know all the mesh currents, if you want to find the voltage across a resistor, for example, you can do so by using Ohm's law. Likewise, and this is the tough one, if you want to find the voltage across a current source, remember that was the thing that we couldn't solve initially. That was the reason that we have these super meshes, because you don't have an easy way to find the voltage across a current source. But if you want to find the voltage across a current source, once you know all of the mesh currents, you can then do KVL for the mesh involving that current source to find that unknown voltage. And we'll see this in an example. So, important thing here is that you only do KVL for loops involving current sources after finding all mesh currents. So if you look at this algorithm, which steps are new? So on the first page, step 2 sub 2 is new. So these are our new steps. Step 2, where you identify super meshes, is a new step we didn't have before. And then in step 3, when you're writing the equations, writing the KVL equations for the super meshes is new, and writing the source equations for the super meshes is new. The rest of the steps are all the same as for type 1 circuits. Let's do a simple example. In this problem, we're asked to use mesh analysis to determine the power supplied by each source. So the first thing you always do is you identify your meshes. We have 2 window panes. We have a mesh there, and we have a mesh there. Next thing you do is you look at each mesh to determine whether you know the current. If so, you write it down. If not, you assign a variable. The yellow mesh has a current source, but it is an interior current source, so we do not know the current. The current through the yellow mesh is not 4 amps. So instead, we're going to create a variable. We'll call it I sub 1. Likewise, the pink mesh has a 4 amp current source in it, but that does not mean that the current through the pink mesh is 4 amps. If that current source was where the voltage source was on the far right, then we would know the current. But because it is an interior branch current source, we don't. So we have to assign a variable to this mesh as well. We're going to call this variable I2. Once again, because we have this interior branch current source right there, we need to use a super mesh analysis. So our super mesh, we basically are going to come up with a loop that avoids that 4 amp source. So in this case, it's only one loop left, and it's this one. This is going to be our super mesh. Now that we set up the problem, we can now find the equations. There are no regular meshes left that we can do KVL for, but there is a super mesh. So we're going to do super mesh KVL. Let's start right here. I always like to go clockwise. I like to sum voltage drops. So we get 10 times I1, that's a voltage drop across that 10 ohm resistor, plus 15 times I1, it's a voltage drop across a 15 ohm resistor. Then we get to the 5 ohm resistor, and notice that's 5 times I2. So even though it's one big green loop, those are 2 separate mesh currents. You keep the separate mesh currents. So it's going to be 5 times I2. Then we hit a voltage source. We hit the plus sign first. So we get plus 10 volts. And we're back to where we started, that equals 0. We can simplify that equation. It's 25 times I1 plus 5 times I2 equals minus 10. And we set that aside. There are no more meshes to do. We cannot do either the yellow mesh or the pink mesh because of the interior branch current source. All that we could do was a super mesh. But we can write, and we have to write, a source equation. Because we have 2 unknowns, I1 and I2, we need a second equation anyway. And we get that with the source equation. Remember, whenever you have a super mesh, you have an associated source equation. What this is telling us is that this 4 amp source has to equal I2 minus I1. Why I2 minus I1? Because the current source is going up, and that is the direction that I2 goes through that branch, and it's opposite the direction of I1. So we see that I2 minus I1 is equal to 4 amps. So we have 2 equations and 2 unknowns. One there, one there. We can then compile them into a matrix if we wanted it to do it that way. 25, 5, negative 1, 1, times our current vector, I1, I2, equals minus 10 and 4. We can then solve this matrix, and we get that I1 is equal to negative 1 amp, and I2 is equal to 3 amp. One thing to note, this negative sign here, all that this means is that our initial guess that I1 was clockwise was wrong, and that current through that yellow mesh is actually counterclockwise. So at this point, we've now found the current through each of the meshes, so we can now use that information to actually answer the question. The question was not find the current through every mesh, the question was determine the power supplied by each of the sources. So now we use this current information to find what we need to solve the problem. Let's do the easier one first. The power associated with the 10-volt source, P sub 10V. Remember, for any element, if you know the voltage across the element and you know the current through the element, you can find its power. So the 10-volt source, leave it as a block here. You know the voltage across the 10-volt source is 10 volts. The current through this source, this is part of the pink mesh, so you have I2 flowing through it clockwise. I2 was 3 amps, so we know that we have 3 amps going in that direction into the source. So the absorbed power is what? The voltage across it times the current through it. Since the current arrow is hitting the plus first, the current is going into the plus terminal, so it is definitely a plus here. So even though this is a source, it absorbs power. Specifically, it's absorbing 30 watts. Let's do the harder of the two now, the power associated with the 4 amp source. So to find the power associated with the current source, you need to know the voltage across it. But remember, voltages across current sources are hard. So what you need to do is you have your circuit here. And we're going to create a variable, Vs, the voltage across this current source. We need to solve for Vs in order to find the power associated with this current source. So what we're going to do, now and only now, we can do KVL for either the pink mesh or the yellow mesh. It doesn't matter which one. I will do the pink mesh. So notice I did not do a KVL equation here to solve for I1 and I2, but once you know I1 and I2, you can use KVL to find the voltage. So starting at this point down here and doing a KVL equation, we get minus Vs plus 5 times this current. But we know what this current is now. It's 3 amps plus 5 times 3 plus 10 volts is equal to 0. The only unknown is now this unknown voltage, so we can solve for it. So we get that Vs is equal to 25 volts. Once you know that voltage, you can now find the power because you have this current source here. You know the voltage across it was 25 volts. The current through a current source is what? It's the current source value. It's 4 amps and it's going in that direction. So let's go up here now. The power absorbed by that current source is what? The power absorbed is the voltage across it times the current through it. And because that current arrow hits the negative terminal of the voltage, you put a minus sign there. So you get minus 100 watts, or we see that the current source supplies 100 watts of power. So the current source supplies 100 watts. The voltage source absorbs 30 watts. By the way, what does that mean about the resistors? The resistors collectively absorb 70 watts. Here's a more complicated circuit that has a dependent source, so let's do the algorithm for this one. First step is always the same. You identify your individual meshes. There's one there. There's one there. There's one there. Then you look at each mesh and determine whether you know the current. If so, you write it down. If you don't know the current, you write it as a variable. So the yellow mesh has a current source, but it's an interior branch current source, so you do not know the current, so you give it a variable. I will make it a clockwise variable and call it I1. The blue mesh, once again, has a current source, but it's an interior branch current source. You do not know the current. I will give it a variable, call it I2. The pink mesh is a little bit tricky. It has a perimeter current source, however, it is a dependent source. But nevertheless, it is a current source and it's on the perimeter, so we know, sort of, that current. So rather than introducing a new variable, we just put the value of the current source. At this point, we're just going to write it as Vx over 400. You might say, wait a second, that's a variable. Vx is a variable. Yes, it is. We'll take care of that in a minute. But as far as the algorithm goes, it's considered a known current source, and so we do not create a new variable I3. We call it Vx over 400. The next step, because we have a dependent source, you have this controlling variable, Vx over 400, and that Vx is the voltage across the 200 ohm resistor. So the first thing you do is you get rid of the control variable. So what we see, Vx, the voltage across the 200 ohm resistor, is the resistance times the current going from the plus to the minus terminal. So Vx is 200 times I2. Notice if Vx had the plus on the right, Vx would be equal to negative 200 times I2. But because the plus is on the left, the minus is on the right, and that is the direction that our I2 variable is defined, Vx is 200 times I2. Right away then, we can substitute that into this equation. So if this current source has a value of Vx over 400, it also has a value of I2 over 2. So this current source has a value of I2 over 2 amps. Once we got rid of the control variable, we can now write our KVL equations. We don't need to write it for the pink mesh because you have a current source and it's a perimeter current source. For the yellow mesh and the blue mesh, you do need to write KVL equations, but because you have the interior branch current source, you have to use a supermesh. So we're going to now introduce this supermesh here that's going to look like this. And now we're going to do a supermesh KVL equation. So supermesh KVL equation. Let's start down here. I'm going to go clockwise. I'm going to sum voltage drops. I hit a 4-volt battery first, and remember this is the minus and this is the plus. So that is negative 4 volts. Then we go through the 500 ohm resistor. Its voltage is 500 times I1. Then we go to the 200 ohm resistor. Its voltage drop is 200 times I2 plus 600 times I2 plus 400. This 400 ohm resistor is bordered by two different meshes. So the current going in this direction is what? I2 minus the pink mesh current, which was I2 over 2. So this is I2 minus I2 over 2. Once again, the I2 over 2 is the same as Vx over 400 using this substitution there. Continuing through this green loop, we now get the 1000 ohm resistor. The current in this direction is what? It's the direction of I1. It's opposite the direction of I2 over 2. So it's I1 minus I2 over 2. And now we're back to our starting point. So that sum equals 0. If you simplify this equation, you get 1500 times I1 plus 500 times I2 equals 4. We don't have any more meshes or super meshes that we can write KVL equations for, but we have one equation and two unknowns. How do we get our second equation? Once again, whenever you have a super mesh, it should signify that you have to have a source equation. So you have a source equation. And the source equation is basically telling us what this 5 milliamp source dictates. The 5 milliamp source dictates that the current I1 minus I2 has to be 5 milliamps. Why is it I1 minus I2, not I2 minus I1? Because the current source is going left to right, and that is the same direction as I1, it is the opposite direction of I2. Had the current source gone to the left, it'd be I2 minus I1. Or had we defined our current variables I1 and I2 differently, maybe making one of them counterclockwise or both of them counterclockwise, the equation would be different. But the way we define our minus I2 is 5 milliamps, 0.005. It's really important, by the way, when you write these equations, if you have things like milliamps or kiloohms, to convert them to ohms and amps. You have to make sure you have the correct units. If you just write that as I1 minus I2 equals 5, you will get the wrong answer. It's 0.005 because it was 5 milliamps. We can now compile these into a nice matrix. We have what? This equation and this equation. So compiling them into a matrix, let's do the bottom equation first. 1, -1, then 1500 and 500 times our current vector I1, I2 is equal to 0.005 and 4. You solve for I1 and I2. I1 is equal to 0.00325 amps, or 3.25 milliamps. I2 is equal to negative 0.00175 amps. Once again, the fact that this is negative just means that our guess that I2 was clockwise was wrong, and that current flowing through that blue mesh is actually counterclockwise. Finally, the question did not ask what were the two mesh currents. The question asked, what is the power supplied by the battery, this 4-volt battery? So we now can answer the question. We'll do that down here. The voltage across the 4-volt source is, guess what, 4 volts. The current through that 4-volt battery, that battery is part of the yellow mesh. That current is I1, which was 3.25 milliamps. And it's going in this direction here. So that current is 3.25 milliamps. So the absorbed power is the voltage times the current. And notice the current arrow enters a minus terminal first, so you put a minus there, so it's absorbing minus 13 milliwatts. So that means that this source supplies 13 milliwatts of power, and that is our final answer. When you have dependent sources, you really only have one additional wrinkle, and that is having to write an equation to get rid of the control variable. Remember, the ultimate goal is the only variables you want in mesh analysis are these mesh current variables. Just like in nodal analysis, the only variables you want in your equations are the node voltage variables. At this point, we're ready to ask the question, which is better, nodal analysis or mesh analysis? Well, there's no easy answer because it depends upon the situation. So let's talk about a couple things here. So the first thing you want to look at is applicability. Nodal analysis can be used for any circuit, any complexity. If you have a circuit, it does not matter how many nodes there are, it does not matter how it's laid out, it does not matter whether it could be planar or not, nodal analysis always works. However, the mesh analysis algorithm only works for a planar circuit, one that can be drawn 2D. So the first issue is applicability. Nodal analysis is always applicable, mesh analysis not always applicable. In this course, we will not have any non-planar networks, so it's not going to matter, but in the real world, you could certainly have some non-planar networks where mesh analysis just does not work. Second thing you want to look at in deciding which algorithm is the one you want to use is what you're ultimately looking for. So the information that's being sought. Obviously, if you're looking ultimately for node voltages, you get those directly using nodal analysis. So if you're looking for node voltages, nodal analysis makes more sense. Likewise, because you can find voltages very easily in nodal analysis, suppose you want to find the power supplied by a current source. You know the current through a current source already, it's a given, and the voltage across the current source is easy in nodal analysis. So if you want to find power supplied by a current source, nodal analysis makes more sense. If, on the other hand, you want to find currents Or if you want to find the power supplied by a voltage source, mesh analysis makes more sense. Why does mesh analysis make more sense if you want to find power supplied by a voltage source? Remember, you already know the voltage across a voltage source, it's the given value. The current through the voltage source in mesh analysis comes directly. If you use nodal analysis and wanted to find the power supplied by a voltage source, you would have to write additional KCL equations. That's sort of that final step in the nodal analysis algorithm. Likewise, if you wanted to find the power supplied by a current source and you were using mesh analysis, you have that added step at the end. Let's go back a couple pages here, sort of remind ourselves of that. To find the power supplied by the current source here, we had this extra step at the end, if you remember. We had to do a KVL equation after we found all of our currents in order to find the voltage across the current source and likewise the power. Had we used nodal analysis, we would have known the voltage across that current source directly. So that's what these two statements here are related to. The biggest thing you want to look at, though, ultimately is the number of equations you need. You'll see in an example in a minute that the number of equations might vary from nodal analysis to mesh analysis. So if one method requires fewer equations, it might be the one to use. Finally, there's a reality that some people find nodal analysis easier to understand and some people find mesh analysis easier to understand. And so ultimately, you may want to choose the method that you are least likely to create errors with. In my years of teaching, I have found that most students find nodal analysis to be easier to understand than mesh analysis. However, I say this, but then I always poll my class, and even though nodal analysis typically has the majority, it's not a huge majority. So maybe I need to get rid of this statement here. Personally, I find nodal analysis easier to understand, and I'll tell you why. So with nodal analysis, your variables are these node voltages. These are very physical voltages. In other words, if you took a multimeter and measured the voltage at different points in a circuit, those are these node voltages. However, mesh currents are not physical. The physical currents are the branch currents, the currents through the devices. A mesh current is an artificial current because it's the swirling current through a circuit, and you have two mesh currents together that create the physical current. For this reason, I find nodal analysis easier. What I want to do in this last problem in this lecture is I just want to count the number of equations needed to solve a particularly large circuit using both nodal analysis and mesh analysis to show that the number of unknowns and the number of equations is not necessarily going to be the same. So here we have a circuit, has a dependent source, 3 different independent sources, and a lot of resistors. And we're asked to determine whether nodal or mesh analysis is preferable for the circuit. In other words, we want to find which one has fewer equations. So let's look at nodal analysis first. Now with nodal analysis, it's tricky because if ground is not predetermined, where you put ground could dictate how many equations you have. So we're actually going to have 2 different situations we're going to consider. First, we're going to consider nodal analysis with ground on the bottom node. So we have ground down here. So we have a node here, this big ground node. Then you have a node here. Another node here. And finally, a node there. So let's look at each node and determine whether we know the voltage or not. If we do, we write it down. If we don't know the voltage, you write a variable. So the yellow node, we know it's 0 volts. It's ground. Green node, is it attached to a voltage source? No. So give it a variable. Let's call it VA. The blue node, do we know the voltage? Well, it's connected to a 100-volt source, but because that 100-volt source is not grounded, we do not know the voltage, so we have to give it a variable. Let's call it VB. The pink node, do you know its voltage? Once again, it's attached to the 100-volt source, but you better not say that that voltage is 100 volts at the pink node because the negative terminal of the 100-volt source is not grounded. So this is another variable, VC. So we see that we have 3 variables, VA, VB, VC. So we're going to have 3 equations. The specific equations I'm not going to write, but I'll write down what types they are. We are going to have a KCL equation at the VA node. Then we're going to have a super node here. And notice we had to extend it all the way down to this because this is all one big node. So basically that current plus 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 that current has to sum to 0. So we have a KCL equation at the supernode. Finally, whenever you have a supernode, you have an associated source equation. So the source equation would be what? Vc minus Vb is equal to 100 volts. So we have a source equation. So if ground is on the bottom, we're going to have 3 equations and 3 unknowns. I'm going to erase all this now and see what happens if we put ground somewhere else. If we ground the 100-volt source, let's see what happens. So now let's put ground there. So once again, let's identify our nodes. There's a node there, a node there, one there, and one here. Now let's look at every node. We know the voltage at the yellow node is 0. The pink node, because this 100-volt source is now grounded, guess what? We know the voltage at this node. It is 100 volts. Do we know the voltage at the blue node? Nope. Let's give it a variable. Let's call it V1. Do we know the voltage at the green node? Nope. Let's give it a variable. Let's call it V2. Notice just by changing where ground is, though, we've reduced the total number of equations by 1. So with nodal analysis, if you are given the option of putting ground to ground a voltage source, you typically want to do that because it will reduce the total number of equations that you have to write. Depending upon how the problem is defined, ground may be predetermined for you. But if it's not predetermined, you can pick ground where you want. So you have 2 equations. What these equations are going to be is you have a KVL equation for the V1 node, and you have a separate KVL equation for the V2 node. And the total is 2 equations. Now let's look at mesh analysis. So we have the same circuit here, but now we're going to use mesh analysis. So the first step is you define all your meshes. There's a mesh there, one there, one there, one there, one there, and a final one there. Now we look at every mesh to see whether we know the current or not. That'll determine whether we have to create variables. The yellow mesh, do we know the current? Yes, we have an exterior branch current source. We know this current. It is 4 amps. How about the pink mesh? No current source at all. You don't know the current. Variable, call it I1. Green mesh. You have a current source, but because it's an interior branch current source, the current through that green mesh is not 2 amps. It's a variable. Call it I2. Same thing with the blue mesh. Do you know the current? Nope. Variable, make it I3. The yellow mesh with the red tick marks, do you know its current? No, there's a current source, but it's an interior current source, so you do not know the current, so it's a variable I4. Finally, the green mesh with the red tick marks, do you know its current? No, it is an interior branch current source, so it's a variable itself, and that's going to be I5. So for mesh analysis, we're going to have 5 equations. And what are the equations? You have a KVL equation for the I1 mesh. You're going to have a KVL equation for the I2, I3 supermesh. That's this supermesh there. You're going to have a KVL equation for the I4, I5 supermesh. So we have 2 different supermeshes in this problem. So KVL for the I4, I5 supermesh. So this will be pink with the red tick marks. Finally, every time you have a supermesh, you have an associated source equation. So the 2 amp internal branch current source is going to give us a source equation. It's what? I3 minus I2 is equal to 2 amps. So we're going to have a source equation for the 2 amp source. And then the current controlled current source. It's a current source. The fact it's dependent doesn't change the fact that it's a current source. We're going to have a source equation for that. And that's where we get our 5 equations from. KVL, supermesh KVL, supermesh KVL, source equation, source equation. So if you look at this problem here, you can do 5 equations and 5 unknowns for mesh analysis. You can do 3 equations and 3 unknowns with nodal analysis and ground on the bottom. Or if you judiciously choose your ground node, you can get by with 2 equations and 2 unknowns. One of the nicest things about nodal and mesh analysis is when you're practicing these algorithms, you basically can get 2 for the price of 1. So for example, if you have an example done using nodal analysis, guess what? You can redo that example using mesh analysis. Your final answers are going to be the same. All the currents and all the voltages are the same regardless of the method that you use. So if you have an example in the book or in the notes done using nodal analysis and you want to practice mesh analysis, try doing it using mesh analysis and see if you can get the same answer. Likewise, if you have an example that uses mesh analysis and you want to practice nodal analysis, you can redo that problem using nodal analysis to give yourself more practice. On an exam, same thing. If you had enough time, you could do a problem 2 different ways using nodal analysis and mesh analysis, and your final answer should be the same. Now, in the reality in taking an exam is you don't necessarily have the time to do a problem twice, but in cases where you do, that's a nice thing about nodal and mesh analysis. You can use either one to solve the vast majority of circuits. Only time this would not work, of course, is if you had a non-planar circuit, in which case you could only use nodal analysis. So this ends the packet of notes dealing with nodal and mesh analysis. For people who like very algorithmic approaches to circuit analysis, you should like nodal and mesh analysis because they're very precise algorithms to follow. Next class, we're going to switch gears a little bit and talk about a new device called the operational amplifier. And we will be spending multiple lectures on the operational amplifier. We will see that the op-amp, as it is commonly called, greatly increases the number of interesting things that you can do with the circuit. For now, we are done with nodal and mesh analysis. Have a good day.